thank you to the organizers for putting so much effort in this event. It's going really smoothly. And thank you to all the rest of you for holding on in this afternoon session. And I'm going to talk about electron shuttling in a silicon double quantum dot. And certainly you've seen enough pictures of quantum dots in this session, in Menno's talk, in Daniel's talk, and also by Irina. So I'll just briefly flash a schematic here. But let me remind you that these quantum dots have an extensive amount of wiring outside for the metallic gates and also for the control electronics. And in some pictures you have seen indicated the charge sensors, which are actually of the same size as a quantum dot. And all this together makes it really hard to scale up those quantum dot devices, in particular if you want to go to 2D arrays. But of course, you want to do that. This has been properly explained by Menno, so I won't repeat it here. I can't do it better than he did. But still, we want to do it somehow. And we hope that our approach of spin shuttling could be part of a solution to address this problem of scalability, because this is a way to introduce interaction between spin qubits on an intermediate distance, that is some microns of distance. And this is done by physically moving the electron between adjacent quantum dots. For example, if you have 1D chain like I plotted here, then you would physically move the electron along this chain by, for example, time-dependently tuning the gate voltages such that the electron is conveyed through this array. This has also been investigated in some experimental studies. And the long-term goal, of course, is that we could scale up our quantum device, for example, by having separate nodes on the chip connected by some of those 1D arrays where the electrons just moved around and transports information, or that you could, for example, just here in the first dot perform some 1-qubit gate, then shuttle the electron somewhere else, perform a 2-qubit gate, shuttle it to the detector, measure it, and then bring it back to just park it there for the next computation cycles. But here in our study, we simply focus on the theory of an elementary unit of a shuttling protocol that is just one transition between two quantum dots in a, that's called a double dot. And we just have one electron which is conveyed from the left to the right by a single detuning ramp. And to assess the success of the protocol, we assume that a spin state is prepared in the left dot, and we compute the probability to find the very same spin state in the opposite dot at the end of the ramp. And that's what I'm going to call fidelity, or more precise, the spin shuttling fidelity. And to compute that in our model, we include basic double dot ingredients such as the energy detuning between the left and the right dot, the tunneling between the two dots, and also the Zeeman splitting. And on top of that, we include a magnetic gradient. We have already learned in previous talks that this is quite big an issue and that this is of course there. And we also include spin-orbit interaction. And then to make the model complete, we have to assume that in a spin shuttling experiment, the electron is prepared in the left dot, but it does not know what comes at the end of the protocol. So we have to assume that we apply a basis transformation where the spin Hamiltonian in the left dot and the right dot are simultaneously diagonal. And in this basis also, we have to keep in mind that the transverse magnetic gradient, which is the Bx here, this can introduce a spin flip tunneling because the local magnetic fields, the Bl and Br, are not necessarily collinear between the two quantum dots. And summarized in the language of energy level diagrams, a protocol now breaks down to preparing a spin state down here on the left side and bringing it over there to the right side, and hope that it's still the same spin state. And we assume here now for the rest of the talk that the level velocity of that detuning sweep is set to a value where the charge, just if there were no spin, only charge, then this charge would be shuttled with a fidelity of 10⁻⁵. This is perfectly realizable in experiments. and then we switch on the spin and check what happens. And to do that, we numerically solve the Schrödinger equation and compute the infidelity, 1 minus the fidelity. And here this is plotted as a function of the transverse magnetic gradient and the Zeeman splitting for the excited spin state as input state. And first up, we see that there is a line with almost perfect spin shuttling. This is where the spin flip tunneling vanishes. And we also see that there are here these local extrema. This is where, due to a Landau-Zener process, the spin flip, not the spin flip, where the spin can make a flip instead of the charge doing a charge transition. This is because the excited spin state has two different paths for the same shuttling outcome, and the probability to take either of those paths, they can interfere, resulting in those spots here where the electron is not shuttled at all. And you can see those dips of the fidelity or the peaks of the infidelity in a line cut along this dashed line, which is the solid curve over here. And now it's clear that there's some asymmetry. This is due to the spin-orbit interaction, which is switched off in the dashed curve for comparison. And this asymmetry is due to the fact that the transverse magnetic gradient and spin-orbit interaction have pretty similar roles in our Hamiltonian. And here on one flank, they are the very same, both enhance the infidelity, while on the other side, they have opposite signs and thus partially cancel out. And we have, even with spin-orbit interaction, a lower infidelity than we would have without. And reversely, this means that by carefully tuning this magnetic gradient, one can eventually cancel out destructive spin-orbit effects which come from the material. And also in this plot here, the red line is basically the very same, just now for the spin ground state as input. And there's no interference fringes for this state, because there's just one path for each shuttling result, at least if you just do a single ramp. So in a real experiment or a quantum computation, however, this is not sufficient, of course, because you don't want to shuttle binary spins just up and down. You want to move superpositions. And the example is for the even superposition of up and down into equal probabilities. And of course, these are now non-stationary states, meaning that the result in the final quantum dot on the right side oscillates between the even and odd superposition, which is the black and green line in the background. And these oscillations are modulated by some pattern, which is best understood by looking into the projections to the upspin and downspin, which is the blue and red line. And then there we see that these are basically the same patterns that we've just seen on the previous slides, even with those interference fringes here, just now scaled to 0.5 because of this prefactor. And on top of this, pattern from the previous slides, from the binary spins, we have some additional oscillation. And this is easily understood by the fact that now in our level diagram picture, we have population not only in one of these states, but in two. And due to the spin flip interactions that has been introduced by the gradient or by the spin orbit interaction, these populations can also interfere among themselves and thus give some cosine modulation on top of the interference term that we have seen before. So, and that now explains what you would see here with the superposition state, and all the effects combined then give the black and green curves to some wiggly modulated probabilities. So, however, this is just a single shuttle going from the left to the right side, and you see that the interference, how is it called? You see that the infidelities can be quite low, and to access them in an experiment, you might want to go back and forth over and over again to get some accumulated effect. And this is what I show you here on this slide. We have simulated a sequence of round trips, and here, even though this may seem very long, this can be done actually much faster than the relaxation time, just a couple of nanoseconds per ramp. And that means that this loss here is due to non-adiabatic transitions into higher states. And the oscillations that you can see here are basically the same as Landau-Zener Stickelberg interferometry, because the same avoided crossing region is traversed over and over again, and the state interferes with itself over and over again. But of course, this is only visible if the coherence of the quantum state is maintained during the entire protocol. And to test that, we include a source of decoherence, that is an electronic reservoir beneath each quantum dot, and they interact incoherently. And in effect, that means there is some additional infidelity due to a spin-flip co-tunneling process, but also now decoherence damps out these oscillations quite quickly. So far, so good, but certainly there are some condensed matter physics experts in the audience, and I guess the chat is already screaming at me that I've been lying to you, because silicon has a 6-fold degenerate conduction band minimum, and in a 2D structure, this is partially lifted into a pseudospin ground state manifold, which I've not even mentioned so far. And to include that in our model, we introduce a valley splitting for each quantum dot, and some angle theta between the valley pseudospins, some kind of valley phase difference you can imagine. And this angle here now gives rise to a valley flip tunneling term, pretty similar to the spin flip tunneling. That means if the excited valley state is prepared, then we can also see some of these interfering paths, which here in the same plot, just a magnetic gradient and Siemens splitting again. Now for the excited spin and valley state. Now we have those interference fringes that we've seen before from the spin flip, but there's new ones here and here, and also in the next highest order here, due to some valley flip transition. And close to these spots, a spin conserving valley flip is much more likely than a charge transition, meaning the electron is not shuttled again. And the occurrence of these terms quite sensitively depends on this valley phase difference or valley angle, which you can see in the insert here. And now let me spend the final minutes of my talk just giving you some insight how we investigated these interference terms here. That was by doing an analytical estimation, making an approximate model by breaking down this complex level diagram of the Hamiltonian into a set of effective two-level systems by applying Schrieffer-Wolff transformations. And to these effective two-level systems, we of course can then apply the Landau-Zener model and calculate the Stokes space and estimate the fidelity. Here we look into the charge fidelity to investigate those spots where the electron is not shuttled at all. And here you can see the result as a function of the two valley splittings of the left dot and the right dot. The background here is a numerical result, and the red and blue lines are indicating where the interference fringes should be situated coming from our model. And you see that this is a quite good agreement unless the valley splittings become too large. For example, here and also here are deviations. This is where the approximations made here break down, but otherwise this is quite good a model. And thus to conclude, just let me say, I've shown you that high fidelity spin shuttling is in principle feasible, even with non-optimized parameters such as I used here. If, however, you were to shuttle the excited spin or valley state, then you would see some interference effects due to Landau-Zener effects in a fast protocol, that is. Constructive interference is really good because it gives you a really high shuttling fidelity. These were the spots where you had almost perfect shuttling. Destructive interference, however, is really bad if you want to shuttle your electron, actually, because these are the spots where the electron is just not shuttled, it remains in its place. If it was in the excited spin state or valley state. But you can imagine to apply these just to implement some kind of spin filter and have spin selective shuttling. And we furthermore developed an approximate analytical model just to check out and to investigate this multi-level Landau-Zener problem, which it basically is. And with that, let me conclude. And again, thank you for your attention. And now I would gladly take any questions that you might have.
Thank you very much for the nice talk. Yeah, for the audience, please do post your questions to the Zoom chat or to Discord. In the meantime, I can start asking. So I'd like to understand better what is the simplest quantum computing task with quantum dot spin qubits where you would need this shuttling. What would be the task? How many dots would you have? How many shuttling would you need to do for completing that task?
That's kind of a mean question, I would say, but
is it?
I mean, we did not really look into some direct applications, but sure, I can answer it. It depends on how your quantum dot device is designed, and of course you can do some 2-qubit processor. You already have mentioned one of those papers by Thomas Watson. There was another one by Dave Sajak in the same year, 2018, and of course there you would not need some kind of spin shuttling. Spin shuttling is not really related to quantum operations in itself. It's more like some optimization procedure. If you have a stretched out quantum processor, you just don't have space for a charge sensor on each dot. So you put just a couple of charge sensors for multiple dots, and then you move electrons like in a CCD to the charge sensor and read them out, and then bring in the next electron and read that out. So you can, for example, if you have 3 dots and you can measure only in one, you do some 2-qubit gates on all three qubits, and then you sequentially measure all one by one. That would be the minimal application I could think of.
Mm-hmm. Thanks. I didn't want to be mean. I was just
no, it's just fine. It's just not a question we've been addressing, but
I see.
Certainly it's of huge importance.
Okay. So Devdut Sharma has a question. Can we use photon or laser shuttling? I can try to interpret the question. Maybe photon assisted tunneling can be something useful, better than this like DC pulse based tunneling.
I mean, yes, this could be possible. I don't see why it should not be possible, but then you would have the requirement to add some components, and this is part of the elegance of this protocol, that you just don't need any more stuff that you don't already have.
Mm-hmm. I had another conceptual question. Can you clarify what is your goal? So the fidelity is somehow your figure of merit, but I didn't really understand. So is it the goal to take a spin state and transport it to the other dot as it is? Or is it better if you take the ground state, for example, in the left dot, and you transport it as the ground state of the right dot? These are two different goals. Which one are you pursuing? Which one is incorporated in your fidelity measure?
It's the second one. So we have a spin ground state and spin excited state in the left dot, and we want to find the same spin state, or at least somehow recover the same spin state in terms of the other dot.
Okay, but then it's not the same spin state, right? It's
not the same.
The same superposition of the ground and the local ground and excited state.
It's not the same spin orientation, but it's like in the same spin quantum number, I would say.
Mm-hmm, mm-hmm, mm-hmm. Okay, clear. Thank you. Okay, so I think our time is up. I'd like to thank Florian for the nice talk, and also for the other speakers.